Right. Maximum average pass ratio. There's a school that has classes of students, and each class has a final exam. You're given 2D integer array classes where classes I equals pass I, comma total I. You know beforehand that in the ith class there are total sub I total students, and only pass sub I number of students will pass the exam. You're also given an integer extra students. There are another extra students, brilliant students, that are guaranteed to pass the exam. Guaranteed to pass the exam of any class they are assigned to. You want to assign each of the extra students to a class in a way that maximizes the average pass ratio across all the classes. The pass ratio of a class is equal to the number of students of the class that will pass the exam divided by the number of students in the class. The average pass ratio is the sum of the pass ratio of all classes divided by the number of classes. Return the maximum possible average pass ratio after assigning the extra students. Answers within 10 to negative 5 will be accepted. Okay, so classes 1, 2, 3, 5, 2, 2, extra students are 2. So this is 50%, this is 3/5, 60%, 100%. So it doesn't make sense to assign students here. I assume you want to assign it here. If you assign one, it becomes 2/3, and then if you assign another one, it becomes 3/4. So you make this 3/4, 3/5, and 100%. You assign the 2 extra students to the first class, and then the average is that. Classes, 4 extra students. Okay. Trying to think what is the best way of assigning students. So if it was a class that had 0 out of 10, the first, let's say 0 out of 10, so one student assigned there would be 1 out of 11. Would make the pass ratio 1 out of 11. So let's say that a certain class has A over B, and then if you assign it, it becomes A plus 1 over B plus 1. And would you just try to always increase? Would you always assign students such that this number increases as much as possible? Like let's do A plus 1 over B plus 1 minus A over B. That would be multiply the first and get common denominator, so it would be A plus 1 times B over, or that'd be the first fraction numerator. And then the second fraction numerator would be A times B plus 1, and then the denominator is going to be B times B plus 1. I'm kind of ignoring parentheses. So if I distribute, it'd be AB plus B minus AB minus A all over the denominator, B times B plus 1. So it'd be B minus A over B times B plus 1. So if you had something that is, let's say 7/8, or 8, 8, let's say it was originally 9/10. So you had 10, 11 minus 9/10. So the answer should be, multiply the first one by 9 over 9, no, by 10 over 10, so it'll be 100. Multiply the second one by 11 over 11, so minus 99 over 110, so that'd be 1 over 110, which is b minus a, where b is 11 and a is 10. B is 11, a is that right? B is 11. The denominator should be b times b plus 1, so that'd be 11 times 12. No, whoops, no. A, B. A is 9, B is 10. Okay. Yeah, so this is b minus a is 10 minus 9. And then, but I'm not sure if that's the way I should be assigning things. Return the maximum possible average pass ratio after assigning extra students. So I could, what is the constraints here? Number of students 10 to the 5th. I don't think it makes sense assigning it. I don't think it makes sense assigning it one by one. Assigning, you never assign to a class that's already 100%. That's stupid. I think and I don't think you always want to assign to the lowest percentage, because the lowest percentage could be like 1 out of, let's say 0 people pass out of 1,000 in the class. Then if you assign to that class, you're getting a bump of like less than 1%. Whereas if you had another class that was, let's say, 5 out of 10, even though it had a higher percentage, you still want to assign to that. So not correct to always assign students to the lowest percentage class. I think you do want to assign to the class that gives you the highest increase. I think it might be this formula, this b minus a over b times b plus 1. You assign to the class that gives you the highest increase in the percentage when you assign to that class. And then you do it for 10 to the 5th times, like you find the lowest class that has that issue. Can do that. So it's on the b minus a. I'm somewhat confused as to why it seems like shouldn't this be a fixed amount when you assign to a class a passing student? The increase, how is the increase dependent on the number of students that are already passing in the class? So if you go from 0 out of 10, let's say you go from 0 out of 10 to 1 out of 11. 1 out of 11 is like 9%, 9.1%, 9.19, 9.1, 9.09, 9% or so. If you go from 9 out of 10 to 10 out of 11, 10 out of 11 is 90.9090. So, I mean, it's still increasing by 9% increase. So it's the same increase, right? It's the same denominator. So when you just assign to the same, when you assign to the lowest, the class with the lowest denominator, assuming that the class is not full, not 100% passing, 9 out of 10 to 10 out of 11 versus 0 out of 10 to 1 out of 11. What's going on here? B minus A. So when you have a fraction A over B, the increase is B minus A. One out of 10 to 2 out of 11. 2 out of 11 is well, no, that's not right. Okay, so 2 out of 11 is 18.2%. 1 out of 10 would be 10%. So that'd be 8% increase. So that would be one if this is A over B, this is A over B to A plus 1 over B plus 1. B minus A over B times B plus 1. So if initially, so B minus A, so 0, 10, so A is 0, B is 10, so it'd be 10 minus 0, which is 10, 10 out of 110, which is 1 out of 11. Then this one is A is 9, B is 10. So 10 minus 1 is 1. Wait. Did I do that wrong? Okay, I think I did it wrong. I see. It's 90.91. Oh, okay. Yeah, this is, whoa, wow, that's really bad. This is an increase of 0.9%. 90% is 0.9. Okay, so it's not actually identical. So the closer to 0 it is, the bigger the gain. Closer to 0 it is, the bigger the gain. But the thing would be here, b minus a I think for each class I should probably do what the gain would be for adding a student in that class, and then I go through the classes, add students to those classes until it matches the next class. So using a heap, uses the heap, it'll iterate, it'll be basically 10 to the 5th speed. Maybe, I'm not sure if it could be slightly faster than that. Okay. And the heap is sorted by the most gain. Most gain. So if this was 0 out of, well, let's say it's 1 out of 1,000. So A is 1, B is 1,000. And you go from that to 2 out of 1,001. The gain there would be 1,000 minus 1 over 1,000 times 1,001, which is 999 over 1,000 times 1,001. That's a pretty small number. I'm gonna go one more step actually. So a plus k divided by b plus k. If I subtract that from a minus b, so that would be a plus k times b minus a times b plus k all over b plus k times b, and distribute, subtract, ab cancels, left with bk minus ak over b times b plus k. So you can factor out the k. You're left with k times b minus a over b times b plus k. So if you increase by more than 1, like increase by 5 or 10 into the class, then the increase in the percentage is going to be that formula. That number of increase times the difference in the original difference in the numerator and denominator of the people in the class over the number of people in the class times the number of people in the class plus the new people. Huh. If there's a better way of doing this besides what I'm thinking about, which is just adding one student at a time. Can I add a group of students? Can I do a binary search for the correct percentage? Return the maximum possible pass ratio. This is a little tricky. The maximum possible pass ratio is not, so if I do a binary search for that value, it's kind of it's a very approximate value. The maximum average pass ratio. Yeah, I don't think binary search would be correct here, because the pass ratio, I wouldn't not necessarily going to try to increase each thing to be that ratio. Or the optimal way of increasing things is not necessarily just to get everything to be the same ratio. So yeah, I think it's going to be for each class, I consider what the benefit for that class would be. What the benefit for that class would be. Okay. Benefit heap. This could be empty. And how many classes am I dealing with here? 10 to the 5th probably, okay. So I think for every class, which is the, let's say, passing and the total for each class, the benefit heap, the benefit of adding another student that's passing to the class would be given by this formula. So it'd be b minus a, which is total minus passing. Actually, I think I could probably skip out on, I wonder if I should be skipping on classes that have or classes are already full passing. I guess in that case the benefit's 0. Yeah, maybe if I say here, if passing equals total, then just skip this class. Is total minus passing divided by the total times total plus 1. So this benefit is a positive value here, so I think I need to sort it by the biggest positive, so I need to make this negative. So benefit heap, I think it's heap push onto the benefit heap, or let's call it benefits heap of tuples benefit passing total to identify which classes are would have the greatest increase. Would have the greatest increase to add another student, to add extra student. So onto the benefit heap, push. Well, this is the benefits heap. Push the tuple that is negative of the benefit, and then I think I want to just have the passing and total values currently. And then for I in range of the extra students, so take the highest benefit off the stack. So I don't care about the actual benefit right now. Passing total heap pop from the benefits heap, and then calculate the new benefit. So passing plus 1, total plus 1. The new benefit is going to be this thing again. And then repush. And then after it's all said and done, actually if I, let's see, let's say I keep track of the number of things that are all passing because that's going to affect the average. So so then when I'm done here, I need to add the percentages. So I think I need to go through all the heap at that point, just popping stuff off. So I think it's for or while there are benefits in the benefits heap, just pop off the top. Actually, I can just go through each individually. So for every benefits passing and total in the benefits heap, all pass. All passing is not really quite the thing here. This is kind of my sum ratios kind of. So my sum ratios is going to be adding the current ratio, and then I do return the total sum ratios divided by the number of classes. Okay. All right, let's see how this goes. Index out of range. Find extra students. Heap pop. Push and pop. It's passing a lot of the test cases. Oh, it's probably the heap is empty, isn't it? Yeah, it's all 100% passing, I think. Yeah, okay. I think I just need to do a dummy trivial case test. If sum ratios equals the length of classes, return 1, basically, because they're all passing. Otherwise, there should be something to work with in the heap. Okay. Okay. Heap of tuples, benefit passing total to identify which classes would have the greatest increase to add extras. Sum ratios is the sum of the ratios of the pass rates. Sum of pass rates of classes. If all classes are 100 passing, trivial, they return 1. And benefit formula, benefit just the increase in pass rate for one extra student, which equals B is equal to, or benefit equals A plus 1 divided by B plus 1 minus A over B, and then dot dot dot. This eventually equals B minus A divided by B times B plus 1. Push that onto the thing. Have your heap. Okay. Okay. What can I do here? So in summary here, first, understand that the best allocation or of extra students would can be found by adding students individually, students one by one, to the class whose pass rate would have the highest increase from that student. Algebraically, that marginal increase can is equal to b minus a divided by b times b plus 1, where a over b is the original class passing fraction ratio. So can simulate adding students one at a time by using a heap of tuples benefit a comma b to identify which class would have the greatest, kind of smallest, well, in this case it'd be negative benefit, greatest, in this case it'd be smallest, negative benefit, increase for an extra student. And then go through, use a for loop that adds students one at a time, taking the popping off heap the best class, incrementing its pass and total number of students. It's passing and adding back onto the heap, another tuple for the new benefit. Actually, I should probably not do this like this. I think I should do a heap push and pop. Pop and push. Heap, pop, and push. It's an operation that's more efficient than just push items on the heap, then pop, return. I want it to actually be pop, then push. Push the item on the heap, then pop and return this. Heap replace, pop and return the smallest item, then push the new item. Pop and return the smallest item from the heap, then push the new item. Yeah, I should be using heap replace because heaps kind of a data structure where you benefit from keeping the same size, so that it doesn't really change the kind of binary tree that's behind it. So I don't want to do a heap pop here, or I don't think I do. So I think I just want to do benefits at 0, which is going to be the top of the heap. Passing plus 1, total plus equals 1. Yeah, and then here this is going to be heap replace from the benefits heap. Yeah, I think this is right. I don't know if it's actually going to change the speed. Should technically be a little faster. Okay. We can simulate adding students one at a time by using heap of tuples to identify which class would have the greatest smallest negative benefit. Increase for an extra student. Use a for loop that adds students one at a time. Popping off the heap, popping off the heap, the best class, incrementing its passing total, and pushing back onto the heap another tuple. After that loop, find sum of all passing ratios and return divide by and return the average, which is divide that sum by total number of classes. Alright, this time complexity, this should be O of n log n, I'm going to say. Where n is the number of classes. Heap has implicit sorting of benefits, which includes every class. N log n is n log n. You are kind of sorting. I'm trying to think how the number of students affects things. Number of students that you're adding. So that should technically be a factor here somehow. Maybe it's m log n. Yeah, I think it might be m log n, where n is the number of classes and m is the number of extra students. The sorting I think that's right. Okay. The number of extra students affects how many times the top, which is the smallest, needs to be found. Alright, space complexity, this is going to be O of, the heap has the size of the number of classes, so I think it's O of n, as the heap can have size equal to the number of classes.